So we're in this chapter on reacting mixtures and combustion. And we talked about the general reaction equation. So you have reactants and products, and it's a one-way street. So it's not reversible. We're going to consider reversible chemical reactions next chapter. You might think of this one, if it starts, it goes to completion. Okay. We talk about our typical fuels for combustion. Hydrocarbon fuels. Do you have these three memorized? Somebody says, what's methane? Let me tell you what it is. Yep. What's propane? C3H8. And then octane. One of the things it does is it shows a trend of getting larger and larger hydrocarbon molecules. Okay. And there's also a trend on the CH4 has a proportion higher hydrogen with it. Then let's say if I had C8 instead of H18, C8H, if it had the same 4-to-1, it'd be 4 times 8, 32. So what happens is the octane or the heavier ones have a higher ratio of carbon to hydrogen. That's why methane's a cleaner burning fuel. You see that on the side of the bus and all that. Oh, methane, the cleaner burning fuel. A lot of it's because they say, you got lower CO2 emissions. Well, you're just rearranging and breaking bonds to get less CO2 and more H2O in the proportion when you have methane, and less H2O in the proportion when you have, let's say, octane or gasoline. All right, anyway. And we talk about the products. The carbons go to CO2 and the hydrogens go to water. We need to know that. Okay. Where do you get the oxygen from? Primarily from the air. When you get it from air, you've got to bring along the nitrogen. And don't forget 3.76 N2 for every 1 kilomole of O2. How do you get that? That's 0.79 divided by 0.21. True? Sure. That's with a 3.79. There's also a 4.76. What? That says if I want 1 mole or 1 kilomole of oxygen, I have to bring in 4.76 kilomoles of air. So be careful. We talk sometimes kilomoles of oxygen, sometimes kilomoles of nitrogen, sometimes kilomole of air. Okay. Stoichiometric coefficients, we need to be able to balance our reaction equations. Also tells you how many moles or kilomoles in the right proportion for a balanced reaction equation. That's what the coefficients are. Then we talked about having just enough air, theoretical air, such that all the oxygen is consumed and it goes into CO2 and H2O. Or you could have excess air, which means you're going to have a little bit of oxygen left over. Okay? You could have had more fuel. You have excess air. If you have deficient air, well, you don't have enough oxygen. You have too much fuel. That would be what we call rich. Rich with the fuel. And this is what we would call lean. So sometimes if you're an automotive background, you've heard about, the car's running rich. You have too much gasoline for the air that's ingested. Lean it out, okay? Used to do that with a carburetor and a little needle. Here, I don't know. You got to do that on computers in the last 20 years. All right, the air-to-fuel ratio, AF. You can do it on a mass basis or molar basis, A to F bar. And then the fuel-to-air ratio, which is reciprocal. Didn't we cover a lot of ground last time? Let's continue on. There's more ground to cover. So dry product analysis. Sometimes it's traditional or convenient or often done is they'll talk about the molar analysis of all of the products except water vapor. So what happened to the water vapor? Typically water vapor will like to condense out. And if it condenses out in some experimental measurement equipment, then it could pool up and make a mess. So often, if you're analyzing the products of combustion, you condense and get it all out. Then you can talk about the mole fractions of dry air. Not dry air, the dry products, okay? The dry products, okay? So that's what we talk about by getting rid of it, by condensing. Here's a problem. Hexane, a hydrocarbon fuel, C6H14, burns with dry air. Dry air, we're not going to bring H2O in with the air, water vapor in with the air. So if you do, it's an added complexity. Maybe there's a homework problem assigned that has some moisture in the incoming air, but it's just a lot of tedious work. Okay, you can do it. I'm sure you can do it. So it burns with dry air to give products with a dry molar analysis of 10.71 mole percent carbon dioxide, 5.36 mole percent oxygen, and 83.93% nitrogen. If I add these three numbers, do they equal 100%? Yes. Yes, they do. All right. So before I look at all of these problems, like determine this and determine that, I want you to look at that dry molar analysis of the products here, carbon dioxide, oxygen, nitrogen. And I want you to answer a clicker question which says that I can tell from the information given that this problem has excess air, answer A, or it's deficient air, answer B, or C, theoretical air, or D, I need more information. So we know that we have hexane. It burns with dry air. We looked at, somebody reports a dry molar analysis of those three components. Can you tell if it's excess air, deficient air, theoretical air, or I just need more information? Okay? Everybody in? So we'll go ahead and shut it down. Ready to turn it off? Yes. Off it goes. And we look at the results. And the results are split all over the map, huh? Okay, well, let me do this to explain it. If I just quickly write out C6H14, and I'm going to bring in oxygen and 3.76 nitrogen, and if I just do it for 100% theoretical air, then the carbon, all of the carbon is going to go into carbon dioxide. So I'll have 6 CO2s. And all of the hydrogen is going to go into water. So I'll have 7 H2Os. Did I get the 6 and the 7 coefficients correct? Yeah? Does that look good? All right. If I have 100% what we call theoretical air, how much O2 do I get? None in the products. All right? So now I can go back and I can get this coefficient right here if I want to balance it out. I would do that by saying this is 12 oxygens. This is 7 oxygens. 7 and 12. That's 19 oxygens. I need 19 divided by 2. From the oxygen balance, 19 over 2. Okay? And then I finish it out by doing the nitrogen balance, and I'll have 19 divided by 2 times 3.76 N2s. True or false? True. So, right here's the key. What do I have? I got some oxygen. How did I get that oxygen in the products? Excess. Excess. Excess, excess, excess. But so if this was 0, if there was no oxygen, then it would be theoretical air, right? All right. Let's select the right answer and dispose. Did that help? Yeah. Okay, good. So because I cluttered up that page, I'll put the problem and resolve it now on a clean page, okay? So we have this hexane, C6H14, blah, 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 all the same information. Determine the balanced reaction equation. Well, first of all, get the 100% theoretical air equation, the one we just did. So I'll just write it down. We had C6H14 plus 19 over 2 times O2 plus 3.76 N2 goes to 6 CO2s plus 7 H2Os plus 19 divided by 2, 3.76 N2s. Now, I need to get a balanced reaction equation with this information given. So I have to rethink this. I'm still going to be going with a carbon balance, a hydrogen balance, an oxygen balance, and a nitrogen balance. That's how I'm going to get it. But what I'll do is I'll start off with my fuel, C6H14, and I'll leave this one alone for a while, but I know that the proportion of nitrogen and oxygen is fixed. Come on now. So I'll leave that in parentheses for my dry air. And I'll come over here and I'll say what they're giving me, though, is 0.1071 CO2, 0.0536 O2s, and 0.8393 N2s, all just like there's a parenthesis here to give me the right proportion of oxygen and nitrogen. There's a parenthesis here to give me the right proportion of CO2, O2, and N2 as determined by my dry molar analysis of the products. True? So I'm going to look for a coefficient A. I'm going to look for a coefficient A which will multiply all of that inside the parenthesis. Well, at this point, I can just stop and I can say, let's apply a carbon balance. How many carbons are on the left-hand side of this equation? 6, and it's only in the fuel. How many need to be on the right-hand side? 6. I have an equal sign, okay? So 6 is equal to, and I look and I say A times 0.1071 times 1. Is there any other place where there's a carbon over on the right-hand side? No, there isn't. Can I solve for the coefficient A just from the carbon balance? Yes, we do. And we find that that coefficient A is 56.022. Yeah, keep all those digits. It's good to keep them all. So what we find is that this is 56.022. That's A. A goes right there. Okay. The water condensed out before we did the dry molar analysis. So I still need water in the products in the general case. So here I'm going to leave a coefficient B. I'm now going to solve for that coefficient B. What type of balance do you think we're going to do? Hydrogen balance. How many are on the left-hand side? 14. I look. Are any in the CO2? None. O2? None. N2? None. So it's just going to be B times 2. Can you solve for B? Is it 7? Is B 7? So then we come up here and we just replace and say, okay, there's 7. And yep, that's what B went to. B is 7. Okay. Let's do the next balance. Which one? Oxygen balance. And so I don't know C, lowercase c, okay? Not C like carbon, uppercase C, but just a letter C that's unknown. I need to solve for C. Okay, so on the left-hand side, it's 2C is equal to. Then you're going to have 56.022 times, and put a big parenthesis right here, 0.1071 times 2 plus 0.0536 times 2. Close parenthesis plus 7 times 1. One equation, one unknown. We can solve for C, and C comes in to be 12.5. So now we come up here and we put in 12.5. What is 12.5 as a ratio? Something over 2. What is it? 25 over 2, is that correct?
Yes.
So I like to work with 25 over 2 because I had 19 over 2 for the 100% theoretical error. True? So at this point, can I box this and call this the answer to part A, which is now my balanced reaction equation? Okay? Now, what about part B? It says percent theoretical error. We already determined that we expected excess error, right? So what is its percent theoretical error for this problem? Well, you're bringing in 25 over 2. And what's needed to be 100% theoretical is 19 over 2. It's 25 over 19. If I want to work that out as a fraction, I'll work it out as 1.32. I know there's some extra change there, but I would say it's the answer here, the theoretical error. I don't have a symbol for that the textbook uses. Okay? It would be 132%. 132% theoretical error. Do we see how we did that? You compared with how much air really was used to the theoretical error. Okay? So we have about 32% excess. That's what we have, 32% excess air. Part C. What is the air-to-fuel ratio on a mass basis? Well, this was our air-to-fuel. Do I put a bar on that or not?
No.
No bar. It's on a mass basis. So I need to calculate the mass of the air per the mass of the fuel. Is that correct? Air-to-fuel? Which is the number of moles, get rid of this, number of moles of air times the molar mass of dry air divided by the number of moles of fuel times the molar mass of the fuel. True?
Yes.
Okay. Number of moles of air. What is it? 12.5 times 28.97 times the molar mass. Is there something else missing? Well, I needed 12.5 oxygen. I did get 12.5 oxygen. But to get the 12.5 oxygen, how many did I have to bring in of the dry air? 4.76. How many people are going to miss that 4.76 on the final exam? Why is there a 4.76, Professor? I'm confused. Well, to get the 1 kilomole of the oxygen, I had to tag along 3.76 kilomoles of nitrogen. Hence, I ingested a total of 4.76 kilomoles of air. All right, I know that's challenging. You have to wrestle with it, okay? All right, and then we bring in 1 kilomole of fuel. Leave this coefficient 1 in front of the fuel. Don't toy with it. You will be tempted. How many people have solved the homework problem already? Were you tempted to change it? Don't. Leave it 1. And then we just have to get the molar mass of the fuel. Unfortunately, I picked this problem so that in the table A25 as well as the table A1 in this textbook, there is no hexane. It's not available in your appendices. Hexane. The professor won't let me Google it on my smartphone during the exam. Right? So what do? You estimate it. Yeah. So each one of these C's is worth 12. Each one of the H's is worth 1. So 12 times, to get the molar mass estimated, you have 6 carbons and 14 hydrogens. 72 plus 14, 86. 86 kilograms per kilomole. The molar mass of just 1 carbon by itself, 12 kilograms per kilomole. Hydrogen, just by itself, 1 kilogram per kilomole. That's how you get a very good estimate. Now, somebody goes out and says, I have access to the internet, and I look up, and it's 86.18. So you got it to 4 digits. Well, since we have it to 40 digits, let's put it in there, 86.18. So the air-to-fuel ratio, when you compute it, comes in at 20.0. 20.0. What does that mean? That means I bring in 20 kilograms of air for every kilogram of fuel for this combustion process. 20 to 1 on a mass basis. 20 pounds of air per pound of fuel. 20 grams of air per gram of fuel. All right. How about, this is the answer for part C, right? This was the answer for part B. What is the mole fraction of the water in the products? I'm going to tuck that up here, running out of space, okay? So what is the mole fraction of water in the products? Well, isn't that the symbol Y of V or Y of H2O? It's the mole fraction. Isn't that how many moles of vapor there are, or water? If I look at this equation, there's 7. There's 7 moles of water. And then I have this 56.022 times 0.1071 moles of CO2 plus 0.0536 moles of oxygen plus 0.8392 moles of nitrogen plus the 7 moles of the water vapor. That's the total number of moles of the products. True? If you want, you can bang this out a little bit, and you find that the number of moles for the carbon dioxide is 6. The number of moles of the oxygen is 3. The number of moles of nitrogen is 47. Spot on. Then there's not. You just work it out, punch it out. You'll see it works it out that way. So I calculate the mole fraction of water vapor to be 11.1%. I know there's some more digits on that one, 11.111 or something. But that's close enough. 3 significant digits for the answer on D. What is the dew point temperature for this gas, this product? You confirmed it. Good, thank you. So what is the dew point temperature? Well, I would get the partial pressure of the vapor in that mixture going out. And the way I calculate the mole fraction of vapor in that mixture times the total pressure of the mixture. At this point, you reread the problem statement and you observe they didn't tell you the total pressure. Assume atmospheric. Sometimes it's just say, I'm going to assume it's atmospheric pressure. There's no other information given. True? So you assume 101.3 kilopascal, and you calculate that this partial pressure of the water vapor is right at 11.26 kilopascal. I go into the steam tables. I find where the temperature, the saturation temperature, gives me that saturation pressure of 11.26 kilopascal, and that temperature is 48.0 degrees C. That is the dew point temperature. Now let's talk about the energy balance. Conservation of energy for reacting systems. Well, we have studied energy and the conservation of energy and done energy balances before. But now something's new. It's reacting systems. Things that come in, like a hydrocarbon fuel and oxygen and nitrogen, aren't always the same as what goes out. So it got rearranged. The carbon and the hydrogen were rearranged to produce CO2 and H2O. Now the nitrogen went along and it just either was heated up typically in combustion, or cooled down. It went along for the ride. But if it was simply just analyzing what happened to nitrogen, you'd say, I already know how to solve that problem. Conservation of energy, I know how to do it. But now you have this changing. But let's start and write our general energy balance equation for a control volume where the combustion's taking place. And in that control volume, I'll assume the traditional sign Q dot is in and W dot is out. Make sense? Of that control volume. All right. So if you write the traditional first law, I'm going to go back. I rarely do this because, in Thermo 1 you were beaten up. Hey, you got to write this general equation and then apply it to this particular problem. But I'll write the general equation. The rate of change of energy in the control volume with respect to time is equal to the rate at which it flows in with the heat minus the rate at which it's flowing out across the boundary of the control volume, often in shaft work or electrical power, something like that, shaft power, electrical power, plus the mass flow rate coming in times the enthalpy coming in. Oh, you have multiple streams coming in? Do a sum over all the ins, plus or minus the sum of all the m dot times h is going out. What did we neglect? Steady state, 0. Neglect changes in kinetic and changes in potential energy. Does that look good? Good? No? Yeah. Let's say somebody says, I don't like working in mass flow rates. I like to work in molar flow rates. So do this. I'm going to do 2 steps in algebra. I'm going to put the Q dot and the W dot on one side, and we're going to sum over all the outs of the molar flow rate times the molar enthalpy of each of those that are exiting. And we'll have a subtraction over all the ins, the molar flow rate times the molar enthalpy of all those that are incoming. E exiting, I incoming. Sometimes they say, well, the out, isn't that our product? Sure. Sum over all the products. Sum over all the P. Sum over all the R. I forgot, what is R for? Reactants, all the ins. Okay. Then you do one more step. You say divide all of the equation by the molar flow rate of the fuel. Often we think per kilomole of fuel. So we divide the whole equation by the molar flow rate of fuel. And then we have the sum over all the products, the molar flow rate of that product that's exiting divided by the molar flow rate of the fuel. Well, it's basically that ratio is the stoichiometric coefficient in our balanced reaction equation. That's what that coefficient is. That's our stoichiometric coefficient in our balanced reaction equation times H bar for all of those exiting products minus the sum over N H bar of the incoming reactants. What again is this N? It's N dot divided by N dot F. What's that F for? Fuel. Fuel. So if it's incoming or outgoing, could be you have the stoichiometric coefficient for each of those reactants and each of those products. Does this equation look good? The challenge is I need to get the enthalpy of CO2 exiting. I need to get the enthalpy of H2O exiting. I need to get the enthalpy, molar enthalpy of the fuel, CaHb. What is this A up here? It's the generic coefficient and a generic coefficient. The textbook uses a subscript A and B on this general hydrocarbon. Okay? As well as the molar enthalpy of the oxygen. Now, nitrogen comes in as a reactant as well as goes out as a product. So you got to be careful. You see the N2 on both sums. But often this comes out hot. Just was combusted, hot. And so this enthalpy of the nitrogen going out with the products is not the same as the enthalpy of the nitrogen coming in with the reactants. They come in cold, go out hot. All right. Well, to tie them all together, they introduced the enthalpy of formation. So the enthalpy of formation, H, it's on a molar basis of formation at standard conditions. I know this is a complicated symbol, but H for enthalpy, the overbar for on a molar basis, the F for formation, enthalpy of formation, and the naught for standard conditions. Standard condition is 298. Is that the same as 25 degrees C? And I chopped it off, but it's 1 atm pressure. So you go to a table. Now, I don't think we've used this table before, A25. And it lists a bunch of substances. It shows you the formula. It reminds you or gives you the molar mass if that's the first time you've seen this substance. Now, you can find other tables will have other substances like water's molar mass is known. So it's some information in this tables and other tables as well in our textbook. And then the key, enthalpy of formation, that's that same symbol right there. Notice the units on it. Kilojoules per kilomole. Kilojoules per kilomole. All right, so there's the units. So let's take a look. Oxygen, O2, what is that parenthesis G for? They're telling you, look, at this oxygen's in the gaseous state at 25 degrees C and 1 atm. Reasonable. I would have probably not needed to be told that, okay? But we'll say G is for gas, it's in the gas state. Molar mass of 32 and the enthalpy of formation 0. Why do you think they picked enthalpy of formation of oxygen to be 0? They have to put everything on the same datum point, the same reference state. And so this is relatively what I would be called, in the unscientific, unengineering term, happy. It's content. All right? It doesn't float around. Oxygen does not float around as O by itself. It does not float around as O3. It floats around, it likes to float around as O2 at that temperature and pressure. Okay, now, let's take a look at carbon dioxide. Well, this is CO2 gas, but its enthalpy of formation is definitely not close to 0. Well, because it's a complicated molecule. It's made of the combination of oxygen plus some carbon. True? So they said the reference for carbon, what do you think that parenthesis S is for? It's solid. It's like coal dug out of the ground. Solid chunk of carbon, pure carbon, okay? Has an enthalpy formation 0. Somehow they had to put everything on a level playing field, and then they found out that CO2, if you put C as 0, enthalpy of formation, O2 is enthalpy of formation 0, has a large negative enthalpy of formation. I try to put this on a graph over here. Let me do this. Let me say that right here is 0. Let me put it over here. The units on this are kilojoules per kilomole. But because a lot of these numbers are so big, I'll put 1,000 right there. So this is 0, this is negative 100, negative 200, negative 300, negative 400. Right around here is CO2 in the gas. All right, where is carbon in the solid? 0. Where is oxygen in the gas? 0. Okay. Let's take a look at water. Water at 25 degrees C, I could have it in a liquid form, I could have it in a vapor form. So that's why they have a G and an L. But they have a different value for the enthalpy of formation. Let's just plot it. Negative 242. Oh, that looks like it's right there. Negative 242 for H2O in the liquid. What about the vapor? Negative 296, 286, right around there. H2O in the vapor state. G, right? H2OG. Okay. Let's take a look at methane. Let's kind of put some fuels on the same scale, but we'll group them over here. What about this fuel methane? It's a negative 75. All right, it's right around there. CH4. What do you think? Gas. See, CH4 gas. How about propane? Remember 3 we were looking at? First of all, C3H8 gas. Negative 104. Oh, put it right around there. C3H8 in the gas. Propane, true? Sure. How about the octane? Well, I could have gas or liquid. You know that when you pump it, it's around 25 degrees C. Comes out of that hose into my gas tank in the liquid state. So it's around 208. That's C8H18 in the liquid, as well as around 250 C8H18 in the gas. I'm sorry, liquid is the lower one. That's the gas and then the liquid. Did I mess up the water? No, the water is right. It is backwards. I messed it up too. Sorry about that. Gas and liquid. Thank you. How many people saw that? We're waiting. Sometimes people raise their hand. I say, not now. I have no time for questions, comments, or anything. I'm on a roll. I can't be interrupted, right? Sorry. All right. Now, I put these values up there. There's a whole bunch that I skipped in this table, all right? But I'm going to try and help make heads or tails of this table, okay? It's not easy. Why? Because they're negative numbers. Why negative numbers? Well, when you go to the energy balance equation, typed out, looking clean, this Q dot is traditionally in, positive in. Well, if I have reactants coming in and products coming out, what do you think Q dot is going to be? Negative. It's combustion. It's heat coming out. So right away it makes it hard for me and probably hard for you to work with the negatives because I got negative on negatives. And then you sum them up. All right. Often this term is 0. Think about burning hydrocarbon fuel. Product, a lot of it is CO2, isn't it? This little coefficient in front magnifies the effect of the CO2 because often for the reactants, I may bring in one fuel, one CH4, or one C3H8, or one C8H18, true? But I'm going to get one of those, or 3 of those, or 8 of those CO2s, depending on what fuel I have. So that magnifier is important. It's hard really to give you good insight into the equations of why this is negative and why is it bigger than this one. I'm trying. I will do my best. But also on all the products you have H2Os, don't you? So how many H2Os do I have as a product if I have CH4? 2. How many H2Os do I have if I have C3H8? 4. How many H2Os do I have if I have C8H18? 9. So I've got that N is growing not just for the CO2s, but it's growing for the H2Os. Go back to this table. Look, the largest negative value in of this that I've shown you is the CO2. And when I multiply that by something like 8, and then I add to it something like 9 to a large negative number for water as well, I can get a huge negative number without, don't worry about heating or cooling it. Let's say it magically goes out 25 degrees C and it came in 25 degrees C. This is the deviation from 25 degrees C. That's that H bar, delta H bar. Okay. So I can get a very large negative number. But you have to know where the carbons that went into the CO2 and the hydrogens that went into the H2O had to come from the fuel. And so you have to take that into account. But it's only a 1 here. And those numbers, I know they're big, but they're not going to be overwhelming. They're here or here or here. Look at the magnitudes of these numbers. And then you have a little fix for the fuels. Okay? So this makes a large negative number, which a large negative Q dot heat out, heat release out of the combustion chamber. So there is my hopefully helpful insight into why the magnitudes are the way they are in the table. Ready to solve a problem? I don't think I have enough time to solve this problem.
Next class.
Next class.